Hello, in today's video we're going to look at how to draw and interpret a probability tree. A probability tree is actually used in the case where we have a probability problem involving events that follow each other in succession. So if we have a simple situation in which the first experiment has two outcomes, A and B, suppose the outcome A has the probability P1 of occurring and outcome B has the probability P2 of occurring. Then we have the case of C occurring when A has already occurred with probability P3, and the case of D occurring when A has already occurred with probability P4, the case of E occurring when B has already occurred with probability P5, and the case of F occurring when B has already occurred with probability P6. These values of the probability can be written as P of A, the event A occurring, being P1, P of the event B occurring being P2. In the second set of branches, the situation is no longer simple because the outcomes there depend on what has happened in the first experiment. In the case of P3, it actually represents the probability that C will occur if A has already occurred, and P4 represents the probability that D will occur when A has already occurred. P5 is the probability that E will occur if B has already occurred, and P6 represents the probability that F will occur if B has already occurred. The next thing to note is that the probability of A given B, for instance, is supposed to be probability that A and B occur divided by the probability of B, where this P of A intersection B is the probability that A and B occur. So this formula is very important in the interpretation of probability tree, especially for events that follow the previous ones. Now let us take the case of P3 on the tree diagram. We have said that P3 represents the probability that C occurs given that A has already occurred, and actually P of C given A, according to the conditional probability formula, should be P of C intersection A, which is still the same as A intersection C, divided by P of A. So it implies that P of A intersection C, or C intersection A, should be equal to P of A times P of C given A. So from this analysis, you would now see why each time we have drawn a tree diagram and we want to get the probability of obtaining the outcomes along a particular branch, we just need to multiply the probability values along the branches that give that event. So that in the case where I would have wanted to calculate the probability that A and C occur, I would simply have P of A intersection C, which corresponds to P of C given A times P of A, as already analyzed below, and that corresponds to P1 for the probability of A times P3 for the probability of C given A. In the same manner, the probability of having A and D occurring would simply be the product of the probabilities along the branches that contain A and D, which means P1 times P4. In the case of the branch involving B and E, we have P of B and E, which again corresponds to the product of the probability values along the branches that contain B and E, which is P2 times P5. And in the case of branches that involve B and F, we just have that P of B intersection F equals, again we multiply the probability values along the branches that give B and F, which is P2 times P6. One thing you should note is the points on the tree diagram which have been labeled N1, N2, N3. You can call them the nodes, or the points from where the branches take their leave. Generally, the sum of the probability values on the branches that leave a particular node is always equal to 1. Even if there are 5 branches that leave a node, the sum of all the probabilities in those branches must be equal to 1. In the case of this diagram, node N1 has just 2 branches, and so P1 plus P2 must be equal to 1. So we have P1 plus P2 equals 1. And this is important in the drawing of the tree diagram, especially when filling the probability values on the various branches. In the case of node N2, the branches leaving it produce probabilities P3 and P4. Again, the sum of those 2 probabilities must be equal to 1. In the case where there were more than 2 branches on that node N2, the sum of all the probabilities would still be 1. So we have again P3 plus P4 must be equal to 1. And then in the case of node N3, the branches leaving it have probability values P5 and P6. So again, we should be talking of P5 plus P6 giving 1. So note that we could also have extended branches, so that we have node N1 extending to cover events A and C, or extending to cover events A and D, just like it can extend to cover events B and E, or events B and F. All those events, still, since they are coming from node N1, the sum of all their probabilities would be equal to 1, although they are now compound events. So in that case, we'll be talking of A intersection B, the probability of A intersection B plus the probability of A intersection D plus the probability of B intersection E plus the probability of B intersection F. They all sum up to give 1. Hence, the sum of the probabilities P1, P3 plus P1, P4 plus P2, P5 plus P2, P6 should be equal to 1. So this other case, which involves compound events being added up to give 1, it will be useful in probabilities where we are required to calculate the probability that at least a particular event will occur. When it involves at least a particular event occurring, we usually have many cases to consider, and it might be cumbersome, so that instead of considering those many cases that would lead up to that particular event, we just take instead the few cases that would not lead to that event, and then we subtract from 1, so that the calculation is shortened. Now we proceed to demonstrate with examples what we have learned about the interpretation of a tree diagram. I'm going to consider the case of drawing at random identical items from a bag, usually different colors, so that we see the tricks that are involved in drawing the tree diagram, especially the case that involves drawing without replacement. So in the case of drawing without replacement, I would look at identical balls, of which 6 are red and 4 are white, in a bag. So to draw the tree diagram for the first draw, when you go into the bag the first time, you can have a red ball or you can have a white ball. The probability of having a red ball the first time you go to the bag would be the number of red balls over the total, and the total is 6 plus 4, which is 10. So the probability of having a red ball the first time you enter the bag would be 6 all over 10. And the probability of having a white ball the first time you enter the bag would be the number of white balls all over the total number of balls in the bag. That would be 4 all over 10. Notice how the sum of these two probabilities on the two branches would add to give 1. 6 over 10 plus 4 over 10 actually gives 1. Now in the second draw, I'll be having the number of options increased, because when I have drawn either a red or a white ball and I'm coming the second time, I have the option of having a red ball when the first was red, or a white ball when the first was red, or I could have a red ball when the first was instead white, or a white ball when the first was white. And now to fill the probability values in the next set of branches, we have to be very careful. As we saw in the analysis, what happens in the second branch is influenced by what has happened in the first branch. So these probabilities in the second branches are conditional. We are looking now at the situation where the second ball is red, given that the first was red. So in the case where we are drawing the balls without replacement, it means that if I have drawn a red ball, there is one red ball that is out of the bag already. So when I'm coming the second time, I will meet but 5 out of the 6 that were there, and the total number of balls has reduced by 1. So I have 5 all over 9 as the probability of removing a red ball the second time I enter the bag. Now once I have the probability of having a red ball the second time, it is now easy for me to fill the probability value for the second branch just by subtraction, because in our analysis we saw that the probability values on the branches leaving a particular node will always give 1. In drawing a white ball the second time, I would look at what has happened the first time. In the first draw, it is a red ball that went out, so the number of white balls is still intact. The number of white balls has not changed, so the number of white balls is still intact. And so since it is a red ball that went out the first time, so my number of white balls has not changed because it is a red ball that went out in that upper region of my tree diagram. So the probability of having a white ball the second time would be 4 divided by the total number of balls, which is now 9, because a red ball went out already. So here you would not need to be wasting time or cracking your brain to get the probability of this second branch. Simply go to the first branch and subtract it from 1. So 1 minus 5 all over 9 would give you 4 over 9, as you are supposed to be filling this other branch. Now the trick with filling the tree diagram in the case where the items are drawn without replacement is to always move to the same color and fill it first. Then by subtraction, you would get the next probability value. So on this lower level of the tree diagram, 1 white ball has been drawn in the first draw. So the number of white balls will reduce by 1 and the total will also reduce by 1. So when I come in the second time, I would meet 3 white balls out of 9 balls left in the bag. And by subtraction, I would then fill the probability of having a red ball the second time if the first one that went out was a white ball. So 1 minus 3 over 9 would give 6 all over 9 as the probability value in that second branch. And it really confirms the fact that the probability of having the second ball red would be 6 over 9, because in this lower portion we are looking at the situation where the first ball that went out was white. So if the first ball that went out was white, then the number of white balls must have reduced by 1, but the number of red balls, 6, will still be intact. And that is why coming in the second time to pick a red ball, we would have that there are 6 red balls out of the 9 that were remaining in total in the bag. So that subtraction always gives you the corresponding probability value without any mistake. And now, what are the possible questions that could come after this tree diagram has been drawn? We'll be looking at the first question. Might ask you the probability that the first ball will be red. And then that one is simple. The answer is just this first value, which is 6 over 10 or 3 all over 5. Then they could instead ask the probability that the second ball would be red. In the case where the second ball is red, the situation is no more simple. We have actually 2 options. The option where the second is red when the first was red, and the option where the second is red when the first was white. So we have 2 options: the probability that the first is red and the second is red, or so we add the probability that the first is instead white before the second is red. And as we already said in the analysis, we get these probability values by multiplying the branches that lead to them. So P of R, which means probability that the first is red and the second is still red, would just be the probability that the first is red times the probability that the second is still red. So we multiply the various branches. So we get 6 all over 10 into 5 all over 9 plus the probability that the first is white in the other case, which is 4/10, into the probability that the second is white in that branch, which is 6/9. And when you multiply, you have 30/90 plus 24/90, which gives 54/90, or 3/5. You could also be asked to calculate the probability that your balls will be of the same color. Again, we look at all the options that will give you the same color. We have, it's either you have red and red, or you have white and white. So the probability of having a red the first time and a red the second time, plus the probability of a white and then a white. And then you substitute again the various values, multiply and add as we have done in the case above. There could instead be the case where we are required to calculate the probability that you have different colors. In that case, it's either you have red and then white, or white before red. In those two options, there is a red and then a white, so they are different colors. We could instead have red and white. This still corresponds to P of red before white, or P of white before red. So if the question says the probability that you would have a red and a white color without saying in that order, so if the word order is not mentioned, you have to consider where red is first and white is second, or the case where white is first and red is second. Take note. Or such a question could be one is red and the other white without mentioning order. Then you have to consider the two cases where the first is red before the second is white, or where the first is white before the second is red. Now we could instead have red and white in that order. So where order is mentioned, we just have P of red and then white. The first red, second white. There is order that we need to respect. White before red can no more be considered. Another possible question would be the probability of having at least a red ball. The probability of having at least a red ball, we actually have many options. So we could be talking of P of R plus P of R W plus P of W R. Those are the different options where there is at least a red ball. And this actually could be shortened by simply taking 1 minus the probability of no red ball, which is all white. Remember what we did in the analysis of the tree diagram. We said the sum of all the probabilities of the compound events for all the branches exhausted is always 1. So the probability of red plus the probability of red white plus the probability of white red plus the probability of white white must be equal to 1. And since we need the probability of at least a red ball, we have probability of red plus probability of red white plus probability of white red plus probability of white white, which must be equal to 1. So to save the time of having to calculate many probabilities, we just take the probability of no red at all, which is the probability of white white, and we subtract it from 1. It shortens the calculation. Finally, you could have to calculate the probability that they are all red, given that they were of the same color. In that case, it will be the probability that they are all red intersection probability of same color divided by the probability that they are of the same color. And here the probability of all red intersection same color should be the probability of all red divided by the probability of same color. Remember that all red is the set R. and same color is the set RR and WW. So the intersection of the two is RR. That is why all red intersection same color is simply all red. So this becomes P of RR all over P of RR plus P of WW. Remember, the probability of all red is P of RR, and the probability of same color is P of RR plus P of WW. And from there you substitute your values and do your calculation. And now, before we end the video, we're going to look at the case where in this same problem you were instead asked to draw 3 balls in succession and without replacement. So in that case, in the first draw you would have a red and then a white, 6 over 10 and then 4 over 10. When you come in the second draw, you have a possibility of red and white when the first was red, or the possibility of red and white when the first was white. We already saw that to fill the next set of branches, you go to the same color. In the case of drawing without replacement, the trick is always to go to the same color and fill first, then by subtracting from one you get the next branch so that you don't confuse. So in my next branch, the red balls have reduced by 1 and the total by 1, so it is easier to fill the next red ball, which is now 6 minus 1, 5, all over 10 minus 1, which is 9. By subtraction, 1 minus 5 over 9 would give 4 over 9. When I come to the next set of branches, in the case where a white ball has gone out, it is easier to fill the next white ball, which is done by reducing the number of white balls by 1 and the total number of balls by 1. So I get 3 over 9 as the probability of drawing a white ball the second time. And now by subtraction, I will get the probability of selecting a red ball the second time when the first one was white. So 1 minus 3 over 9 will give 6 over 9. And if I am doing a third draw, I need to be very careful. So I will go again. In the third draw, I have many options coming up. Having a red ball when the previous was red, or a white when the previous was red, or a red when the previous was white, and a white when the previous was white, red when the previous was red, or white when the previous was white, or red when the previous was white, and white when the previous was white. So in this case of filling the third row of branches, you simply look at what has happened in the previous draw. So to fill in this next red branch, I will look at the previous red. It is easier again to fill the next red from the previous red by subtracting 1 up and down. So to have a red ball the third time, I will have 4 all over 8. Then by subtraction, I will now get the case where the white ball is drawn the third time, which again 1 minus 4 over 8 would give 4 all over 8. When I come to the next set of draws, what I would simply do is look at the previous color, which is white. It will be easier to fill the next white. So the probability of the previous white is 4 over 9. I will subtract 1 up and down so that I can fill the next white. When I come in the third time, there are now 3 white balls out of 8 that I would meet. So the probability of a white ball the third time will be 3 over 8, and by subtraction, the probability of a red ball the third time on this set of events in the upper region of the tree diagram would be 1 minus 3 over 8, which gives 5 all over 8. When I come down to the next row of events, so here again I will look at what went out previously, which is red. So the next red would be by subtracting 1 up and down. So I get 5 all over 8. So that subtracting it from 1, I will now have 3 all over 8 as the probability of drawing a white ball in the third draw in that row of events. When I move to the last draw, I will look at the previous one. It will guide me to fill the next one. Since the previous is white, it will be easier to fill the next white in that row. In the next white again, I will subtract 1 at the top and at the bottom, so I get 2 over 8, so that the probability of a red ball in that last row of draws would now be 6 all over 8. And you can see that this 6 over 8 for the red ball that is drawn in this bottom row of the tree diagram is justifiable. Look at what has happened previously, right from the first draw till the end. You would notice that in the first draw a white ball was out. In the second draw again, it is a white ball that went out. The number of red balls are still 6 as they were initially. and that is why in the last draw the probability that you would have a red ball is now 6 all over 8, because in this last row only 2 white balls went out. The number of red balls were still intact. Now the total number of balls is now 8, because 2 white balls had gone out previously and they did not come back because the draws were not being replaced. And so when you do all these tricks, you would always get your probability values correct, and it saves time so that you can easily walk through your exam without time constraints. The set of probabilities that could be asked in this case of drawing 3 balls is that we could be asked to calculate the probability that the first ball would be white, and that would just be this value here, 4 all over 10. Now the probability that the second ball is red, like in the previous case of red balls, we are going to consider RRR or RRW or WRR or WRW. In all those options there is a red ball in the second position, and since the options are linked by the word or, we are going to be adding them to obtain our probability. So this gives P of RRR plus P of RRW plus P of WRR plus P of WRW. So in all these options the second ball is red. And now you multiply the various probability values along the branches and add them to have your probability value. You could also be asked the probability of having the same color. That will just be 2 options: the probability that they are all red or the probability that they are all white. You multiply the probability values at the various branches and add. You could have the probability of having the last 2 white, and that would be, you consider the options again. You have RWW, the last 2 are white there, so P of RWW plus P of WWW. In this one too, the last 2 are white, and then you multiply the probability values on the various branches and add to have your value. We could also talk of probability of exactly 2 white or 2 red balls. There are a series of options. You could have P of R then W, or P of R WR and then P of WRR, and again you multiply the probability values on the various branches and add to have your probability value. We could have P of at least a red ball. Then it will have many options, so we just take 1 minus the probability of no red ball, just like we had in the case of drawing 2. So no red ball actually means all white. So this is the shortest way to calculate this type, which if you were using the other method, it would need that you consider all the options where there is at least a white ball, and there are about 7 options. So calculating 7 options and adding would be quite cumbersome. We could also have the case where we need to calculate the probability that there are at least 2 white balls. So to have at least 2 white balls, we have to look at all the options. We should have either 2 white or 3. So it should be P of RWW, there are 2 white balls there, plus P of WRW plus P of WWR plus P of WWW. So So in all these options there is at least 2 whites, so you multiply all the probability values in the various branches and add them to have your probability value. Now you could also have probability of all white given same color. That will be equal to probability of all white intersection same color divided by probability of same color. And just like we had in the previous case involving drawing 2 balls, probability of all white intersection same color is the probability of all white, and we are dividing by the probability of same color, which is either all red or all white. So that is how you interpret this one, and then you do your multiplication of the probability values on the branches and evaluate the probability value. It is also possible that you are asked to calculate the probability that you draw at least 1 white given that you have drawn at least 1 red. This should be equal to the probability of at least 1 white intersection at least 1 red all over P of at least 1 red. And the probability of at least 1 white intersection at least 1 red, if you look again at the tree diagram, you would see that where there is at least 1 red would be all the branches except same color. So red, 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 there is not at least 1 red and at least 1 white. And white, 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 there is not at least 1 red and at least 1 white in those options. So the rest of the options have at least 1 red and at least 1 white. So to get the probability of having at least 1 red and at least 1 white, we simply take 1 minus the probability of same color. It will give the same result. So the probability of at least 1 white and at least 1 red is 1 minus P of same color all over P of at least 1 red, which is 1 minus P of no red, and no red means all white. So this will give 1 minus P of all red plus all white, or simply minus P of all white all over 1 minus P of white, white. So getting all these probability values on the various branches and substituting, you can be able to evaluate your probability value. Thanks for watching. If you are new to this channel, please consider subscribing and activating the notification bell so that anytime a new video is posted, you would get the alert and then watch. Also comment, like and share the video to your friends and classmates so that they get to know more about the channel, which has a lot of resources concerning your studies, especially of A-level mathematics and further mathematics. In the next video, I am going to present the case of drawing tree diagrams where replacements are involved. There are certain cases of replacement which are complicated. That means you replace with a ball of the other color, or replace with an additional ball of the same color, or replace with an additional ball of the other color. So just like I've shown the tricks that are involved when doing draws without replacement, in the next video I am going to show you how you can draw a tree diagram in the case where complicated replacements are involved, especially the tricks that you will be using to gain time, just like we have learned in this other video. I wish you good luck in your exams.